Hello and welcome to Ashwa's Tech. Today we are going to embark on the journey of containerization. Essentially, we are going to see how we have moved from physical to virtual and then to containers, and that too in the span of 40 years. So let's start from the beginning. In 1980s, the system was monolith, containing everything within: the hardware, the operating system, the software, applications, everything was contained within. And usually, one person used to work on it at a time. But now you can see the problem. It required a lot of space to have a lot of servers, and then it was kind of a costly affair. So then came the era of virtualization. So during 1990s and 2000, a company called VMware started this revolution of hypervisors. If you take the same monolith hardware that you have, you can now break it into smaller virtual machines and everyone can work on it simultaneously. We are going to have a look at it very soon. But this is just in essence what virtualization is. And then came the containerization. This is taking one step further. All the overheads that we usually see with virtualization, those are now removed in containerization. Why do you even need virtual machines and overheads? You can further drill it down. A single physical machine or even VM can be further broken into small applications. Nothing but containers. So imagine having one database server process running in a container. Do you need that service to run as a virtual machine or maybe on a single hardware or physical box? Not required, right? Because just to run one daemon, one database service, why do you have to have one dedicated physical server, or for that matter even a small virtual machine? It can be run within a single container. So you are further breaking it down. So let's go to the next slide. For example, you can see over here that a physical server having 32 gigs of RAM and maybe 32 core CPU, pretty costly hardware. But now what you can do is you can have maybe one person or maybe a couple of person working on it, right? So think of it as a bungalow, for example. However space you have, maybe you probably have a couple of acres of land and you have built this bungalow on top of it. But eventually you are going to have only one family residing in that bungalow. All the resources, everything will belong to this particular family. No matter whether this family really requires that kind of resources or not. Right? So here you can now see that even though we have a lot of property, seldom we will be making use of it completely. And it is really difficult now to justify the investment. So let's go to the next concept, virtualization. Now think of the same land on which you have built a bungalow, but now instead of bungalow you now have a building, an apartment building, right? Here now you can see that on the same piece of land multiple families can stay together in the same building, yet each and every family can have an isolated space of their own, so they don't have to share space with one another apart from the amenities maybe. So here the same 32 gigs of RAM and 32 cores machine is now broken into 5 virtual machines. Essentially you are making better use of the same hardware. In our terms, 6 families can now stay on the same piece of land on which only one family could stay in a bungalow. So this is the beauty of virtualization. You are making sure that whatever investment that you are doing, you are fully utilizing it, and yet each and every family is having their own space. That is the isolation and optimum use of the piece of land. Now let's go one step ahead. Containerization. Now think of it as a hotel. So if you are visiting a particular city, for example, do you really need to have a bungalow in that city? Or probably, do you really need to have an apartment in that city? If anyways you are going to be there only for maybe few days of the month, why do you even have to invest in a bungalow or an apartment? The best way is you can now stay in a hotel. So even though you are getting that isolation using the hotel rooms, you are not exactly owning anything of it. Yet for the period of time that you will be staying in that hotel, you are going to get all kind of privacy, but limited to that space, that room. So think of it as you have a big chunk of server, the same 32 gig RAM and 32 core CPU. With the kernel and services, you have a container runtime shared by all the containers through container runtime. So in our case, for example, the amenities like gym or probably the restaurant space, it will be shared by all the guests of that hotel room. But yet they will have their own isolation when they return back to their room. This is rather how the containerization started. We started with a very big, chunky, fat physical server. Then we thought, oh wait, we are investing too much of our money, but we are not getting bang for our buck because seldom we are able to fully utilize the hardware. So then came the virtualization, wherein now you are virtualizing your hardware. You can have multiple virtual machines, maybe of different operating systems as well, because in case of virtualization, the operating system has its own kernel. It's a full-fledged operating system that you are using on the same hardware. For example, in this case, the VM1 could be Windows, VM2 could be Linux, maybe Red Hat, VM3 could be Ubuntu, and so on and so forth. Each and every operating system is a full-fledged operating system running on the hypervisor, or rather making use of the hypervisor to run on the same hardware. So here the hypervisor layer is virtualizing the hardware that you see over here. Now taking one step ahead, why do you need to have multiple kernels? If you are going to have the isolation only at application layer, and if that is enough for you, you don't have to have that overhead of having multiple virtual machines. In this case, the containers through container runtime, they are going to use the same operating system and its kernel and services using the same hardware. So essentially, if virtualization is to virtualize hardware, containerization is to virtualize the application layer. Of course, the containerization or isolating your applications is not new to Linux. Since ages, we have C groups and namespaces, and containerization is specifically based on these two concepts, namespaces and the C groups. So this is all about the journey of moving from physical server to virtualization to containerization. Now you can think about cloud. Why do you need containers? You can very well run virtual machines on cloud as well. But now think of it, the cost required to run virtual machines in the cloud against the cost required for running containers, there's a huge difference. And of course everyone wants to save costs. That's why most of the cloud applications, they make use of the containers, and these containers are ephemerals, like our guest in a hotel room. They don't own anything, they are ephemeral, they are stateless. Of course you can have stateful containers as well through volumes and all. We are going to get into that, but I just wanted to first map and tell you how we move from physical to virtualization to containerization, so that with this context, in the next chapter we are going to see how things are actually done, and then we will get into the containerization in depth, like how to create your Docker files, how to download and run containers, how to debug them, how to run, for example, a Mongo database and probably a Mongo Express in containers, and then push data into it, view using Mongo Express, and so on and so forth. Let's now see how virtualization differs from containerization, and in particular how virtual machines compare with containers. Let's go through some of the features, like resource consumption. In case of virtual machines, it is medium to high because typically it includes the entire operating system. In case of containers, the resource consumption is low given it is sharing the host kernel. Isolation level, again, very strong in case of virtual machines, given it is at OS level. Each and every virtual machine carries its own operating system. In case of containers, given the isolation is at process level, it's kind of a lightweight isolation. Boot time, given you're booting the entire virtual machine as an operating system, it is kind of medium. Containers are fast to boot because they usually directly run on the host kernel, so it's pretty fast. Operating system, multiple operating systems you can have in form of virtual machines on one physical server. Same is the containers. Even though we call containers, they have their own virtual system. Essentially it is nothing but the overlay file system, while all containers, they run on the same kernel given by the host, so they are not per se operating systems, even though they might appear to be. Portability, in case of virtual machines, it is medium. The images could be large. In case of containers, the portability is high. We can have very lightweight containers. For example, Alpine container is as good as only 5 MB. Density, it is medium in case of virtual machines. You can have multiple VMs per physical server. It is very high in containers because given these are very lightweight, you can have hundreds of containers running on the same physical server. We can quickly jump into my virtual machine manager, where I can show you how I'm running Windows on my Linux host as a virtual machine, as well as another distribution of Linux called Mint side by side. And then I will show you a couple of containers that I have, Mongo and Mongo Express, and we will see how they differ on the boot time as well, for example. So let's move to the virtual machine manager. Okay, so this is my virtual machine manager console. You can see I have two virtual machines created on my host. My host happens to be Zorin, running on Zorin operating system, which is a fork from Ubuntu. I have 32 gigs of RAM running on NVIDIA GPU and AMD Ryzen 5 processor. If I go back, I have just started Mint Linux system. I will start Windows as well, so this will now start booting the operating system. If I open this, you can see now it is booting into Windows. Let me quickly go full screen and log in. So here it is. So right now I am running Microsoft Windows as a virtual machine on my Zorin Linux on the host. If I go and open this, let's say right click on this, properties, let's see. So here you can see that I have installed RAM as 8 GB, and it is detecting my processor and storage. So this is the storage that I have allocated for this virtual machine. Now let me quickly minimize this and probably go to Linux Mint. So this is my Mint Linux operating system. Again, this is running on my same hardware, same physical box on which I have Windows running as a virtual machine. So this is yet another virtual machine. If I do neo fetch over here, you can see that it is detecting it as Linux Mint, and I have allocated only 4 gigs of RAM. So for Windows I have allocated 8 gigs, for Mint I have allocated 4 gigs. Of course this is all 8 gigs and 4 gigs. This is coming from my 32 gigs of memory on my physical host. So this is about operating systems. You can see I'm running Mint and Windows side by side. So this is Windows and this is Mint, while this is my actual host operating system. Cool. So let me clear this out. Now let's go to containers. I have Docker desktop installed. Here you can see that I have couple of images, Mongo and Mongo Express. What I'm essentially going to do is I'm going to run Mongo Express and MongoDB as containers, and you can see over here so this is the deployment. I have Docker Compose through which I have already run this, that's why you see this as a deployment. If I run them now, just look at it, it has started running, hardly took a second. So now if I do this, you can see that it is already up and running since 6 seconds. This is how fast running a container is. There is absolutely no overhead of booting your operating system and all. See, and you can see now that CPU utilization is pretty low. I have 8 core CPU, but it is hardly using even 1 core out of it. And if you see the container memory usage, I'm using only 316 MB out of the 8 gigs that I have allocated for Docker. So this is how lightweight containers are if you compare them to virtual machines. They both solve their own problems, you can say. The containers where you want application kind of isolation, pretty lightweight, fast to run, you can scale out, scale in using Kubernetes. For example, if you have a replica set to, let's say, 50 containers, no matter what, Kubernetes engine will always make sure that you have 50 pods or containers running, and it is pretty automated through Kubernetes. The point that I'm trying to make is containers are pretty lightweight. You can run hundreds of containers on this same physical box, but I cannot do that with virtual machines. I can probably go to maybe 3 or 4 virtual machines looking at the total RAM that I have. But in case of enterprises, what we typically have these days is maybe around 32 cores, CPUs and 1 TB of RAM, wherein a team can share this kind of blade server, creating their own virtual machines simultaneously. Maybe 8 to 10 people can easily work on such virtual machines with good amount of memory, because engineering machines, we typically want more RAM for compilation and all that, and even the computing power. So that's why one blade server is typically shared within the team. You can go from anywhere from 8-10 VMs to 20-30 VMs based on the kind of load that you will be having. In case of containers, these are pretty ephemeral, they come and go as required. So now if I probably just go over here and say shut down, this virtual machine will now shut down. You might have heard that sound as well. So now let's go here and say shut down. See how much time it is taking for shutting down, right? Maybe 3 or 4 seconds. If I go over here and just say stop, not even 1 second, right? If I just do TPS, you can see these are already exited. Okay, so this is all for chapter 1. Please don't forget to like, share, subscribe, Ashwas, and show us your love. Thank you.